students, this is Dr. Rakesh, Associate Professor from Department of ISE. In today's session, I am going to discuss about program number 1 with respect to ADA Lab, Design and Analysis of Algorithms Laboratory. In today's context, algorithm is not so new in the sense we can see algorithms in various applications like Facebook, YouTube, Twitter accounts, Instagram, etc. Why algorithms used is, when you take this particular course, there are different modules are there. Each modules is pertaining to different applications. Okay, if you take divide and conquer, there some algorithms are there. Those algorithms is going to discuss the applications of divide and conquer method in real time, whichever is going to be applied. Suppose if you take the greedy method, in there we have knapsack problem, dynamic programming, etc. There the applications is real time use for that particular example. Then coming back to your dynamic programming, there we are going to use the typical your knapsack problem or your Prim's-Kruskal algorithm, etc. Okay, finally we have backtracking. In the backtracking we use branch and bound. There we use Hamiltonian problems and your N-Queen's problems, etc. Okay, coming back to the today's context, we are discussing the program number 1. Program number 1, it's about binary search. Before I discuss about binary search, I would like to give a brief introduction to algorithms. What is this course is all about, how this algorithm is going to be very much important in today's context of various applications. The objective of the class, algorithm, the criterias, priori and posteriori algorithms and algorithm specifications. This is the objective of our session. The following are the module outcomes. How algorithms are going to be useful in real time, and performance analysis, important problem types, and data structures used for algorithm. Okay. When you take an definition of an algorithm is nothing but it's a procedural steps. It's a procedural steps to solve a problem. Means, if you take an example, I want to perform addition of two numbers. I would like to perform addition of two numbers. In that case, how to solve this problem? Here, step 1, I am going to read A, B, C. Means A is a variable and B is a variable and C is a variable. I am going to read that particular elements. Then step 2, perform addition operation. In that case, C is equal to A plus B. So the second step what we are going to do here is performing the computation of summation operation. The third step what we are going to do is we are printing it, write C. So if you can see these particular steps, okay, step 1, step 2 and step 3 all are nothing but procedural steps to solve a problem. Similarly, the definition says algorithm is nothing but solution for a given problem in terms of a steps manner. What is an algorithm? Just now only I just told it's nothing but a procedural steps to solve a problem. Okay. Some of the requirements for an algorithm as follows: finiteness, definiteness, clarity specified input, clarity specified output, and effectiveness. Suppose for this example, if you take a for loop, okay, for I is equal to 0, I less than n, I plus plus. Okay. If x modulus of 2 is equal to 0, printf even or else odd number. Suppose if you take this particular example, I have written a small looping construct which has a for loop and a if statement. In this case, for the first point, finiteness terminates after a finite number of steps means, suppose if I give the n value is equal to 5, okay, till 5 elements, until the 5 elements is going to get executed, this particular loop is going to continue its execution. That's what we call it as a finiteness. Okay. Definiteness means rigorously ambiguous specified, means I am going to specify this particular loop to execute specified number of times, okay, 5 number of times. What that 5 number of times it has to do it is, I have to find whether my number is even or odd, okay, whether my number is even or odd. In that case, I am specifying the condition without any ambiguity. My condition is very much specifically mentioned here without any ambiguity. Because of that, I am able to execute this particular loop properly. So that's what we say is a definiteness. Clearly specified input. Suppose I have n is equal to 10, okay. In this 10 number of elements, I would like to print 5 number of odd numbers and 5 number of even numbers. In that case, my n is specifically mentioned. That's what clearly specified input is given here. Fourth point is expected output. Expected output means what? When I give my n is equal to 10, okay, for example, or n is equal to 25 for that matter, okay. So between 0 to 24, my array index starts from 0 here in the for loop. Between 0 to 24, whatever the elements that has even numbers, whichever the element that has odd numbers, that will be expected output of the given algorithm. That will be the expected output of a given algorithm. The final one is effectiveness. Steps are sufficiently simple and basic, because see, the algorithm experience is something wonderful in the sense, the more you get drilled into the algorithm concepts, etc., drilled into the concept of algorithm, what happens is you learn the art of writing the programming well, okay. For example, I can declare int a is equal to int a variable I have declared here, which has 2 bytes of allocation in the memory. I can say a is equal to 10, okay. When you start a programming, as initially in the infant stage, what happens is you declare multiple statements. Although it's correct, the declaration is correct, the assignment is correct, but I can also write this particular declaration in these terms: int a is equal to 10. This is also valid. So subsequently, as you proceed with the algorithms and its experience and art of programming, we can reduce the number of steps, okay, with the help of applying the algorithm. That's what it's nothing but effectiveness, simple and basic. So coming back to the same definition, an algorithm will take a real-time problem, okay. We are going to input a computer. The computer contains a motherboard which has CPU in it and control unit, which is going to perform some particular operation, and we are going to get the output. Suppose if I am going to give the input as a is equal to a, b and c. All these are all the values for the CPU, okay. If my condition is to perform c is equal to a plus b, okay, my computer will take CPU, central processing unit. It has ALU, arithmetical logical unit, because it has to perform addition operation. That processing is done by the CPU. And output is shown in the CRT monitor, or your LCD, or your laptop, or your smartphone. Many other gadgets are there in the market. We can also see in that particular as an output, okay. This is about your typical example of an algorithm which has a finite number of steps to solve a given problem at a given point of time. Next, in other words, suppose if you take an example, a real-time example, put the book in the box, okay. For this purpose, if I want to draft or write an algorithm, how to solve this one? First, I have to open the box, then I have to put the book into the box, then I have to close the box. In that case, what happens? These are steps: open the box, pick up the book and close the box. It's a steps to solve a given problem. That's what is nothing but your algorithm is all about. Then the algorithm we can perceive in two aspects. One is the theory aspect of it, second one is pragmatical aspect of it. Theory aspect means you will understand the concept, okay, you will understand the concept, whereas in practical aspect you are going to implement it, using some code. Okay, this code can be C language, C++, Java or Python, whichever the languages, high level languages, we can use it and accordingly we can implement it. Okay, in terms of core computer science concept about this algorithm is what about is, if at all if you take any syllabus, university syllabus or curriculum etc., there won't be a department, computer science department or IS department or the relative the sister concerned department definitely will have this course as part of the curriculum, because this particular course is quite important or paramount in day-to-day activities and applied in a lot of real-time applications. So this subject, this course will be there as part of the syllabus. Then part of the practitioner toolkit to know algorithms etc. The more you dwell into the micro level of algorithms, different types of techniques, methods, mechanisms etc., you will come to know the beauty of the algorithm, and accordingly we can find a feasible solution. Okay, like if you take Facebook, in terms of distribution of the images, categories of the images, and if you take the Ola, Uber kind of route, destinations and source method etc., source and destination etc. in Ola or Uber, okay, we use some shortest cut algorithms, Dijkstra algorithms. Okay, so this Dijkstra algorithm is one of the example of our typical algorithm concept. So in that case we ought to be very much fortunate to know how algorithm is going to be very much predominant in day-to-day activities. Then whenever we write an algorithm, okay, there are two things we have to understand. One is manual measurement, and the second one is system-based implementation. What exactly happens here is, if you take the first one is priori analysis. Priori analysis means whichever the algorithm you take it, okay, you will suppose if you take an algorithm, a for loop is there, a if statement is there etc. It may be for a selection sort, it can be for a radix sort or heap sort or quick sort, merge sort etc. For that matter, if you take this algorithm, okay, I can also write this algorithm manually in a paper or a book etc. I can count the number of times this particular loop is going to execute. So for example, this may execute for 5 times, for example this may execute for 5 times. I can tell my count is nothing but 10. So this is one way of telling my measurement of my algorithm, what is the implementation of the status. Second part is posteriori analysis. Here what happens is a typical implementation into the system, okay, how the algorithm is going to get executed. Okay, whenever we take the algorithm in terms of implementation part, there are many things are involved in this. Okay, suppose if you take a RAM, okay, RAM is nothing but random access memory. RAM is there. We can also call it as main memory. Or we can also call it as physical memory. Okay. So what happens is, whenever we take RAM, which is nothing but main memory, what are the executions of instructions, programs or instructions or any statements executable statements, all are executed in memory space of RAM. Okay, during this time what happens, OS will be part of RAM and CPU is also be part of the execution. Okay, CPU also will be part of the execution, and somewhere our code, whichever the code, it can be prime number, GCD number, and any project application which is developed using C language or C++ language, which will be part of the RAM only. So it will be executing this particular space. Okay, so while executing that particular program in this RAM, we call it as time complexity. Okay, so after executing, suppose if you take an example of a quadratic equation program, okay, it may take around 25 KB, okay, the space of that particular program. In that case, this 25 KB of the program should be stored in some repository. Okay, that repository is nothing but your secondary storage disk, your hard disk. Okay, so the space occupied, this 25 28 KB into the disk is nothing but your space complexity, the amount of time taken to store it into the memory. That amount of time to execute that particular program in RAM is nothing but your time complexity. That is about your priori analysis and posteriori analysis. Next, I am going to discuss in this session about binary search. Okay, we all know binary search is very important algorithm to start with in terms of algorithms. This is our first program number 1, binary search. Okay, what happens in binary search? I'll explain in detail. We have a set of elements. Okay, it has array of 9 elements: 0, 1, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. It has 8 elements, I beg your pardon. And in 8 elements, starting from 0, it is going till 8. Okay, array index always starts from 0. Okay, now these are all the elements: 2, 4, 6, 8, 10, 12, 14, 16 and 18. Okay, the idea in this particular binary search is, suppose I have few elements here: 2, 4, 6, 8, 10, 12, 14, 16 and 18. These, out of these elements, I would like to find a key element. Okay, key element. Suppose my key element can be 14, my key element can be 16, my key element can be 4, my key element can be 6. It can be any element which should be there in this list. If the element is there, we have to find that particular element, whether it is there or not. During this identification of the element is exist in the array of list or not, we have to apply this binary search. How this binary search is applied means, suppose I have few elements, I have array of elements. Okay, I have some array of elements of 0 to n. Okay, this all called as initial low value, and this I called as I value. Okay, lower index or higher index, or small or large. Okay, whatever we can give our conventions, no problem. Low. Okay, what happens here is, I have set of elements in this. In this set of elements, I would like to find key element. Okay, my key element is found or not. X is nothing but here key element. Whether that key element is found in this list of array or not. Okay, if it is found, we say it's found. If it's not found, we say it's not found. Okay, whenever the element is only 1. Okay, whenever the element is only 1 in terms of binary search. Okay, here we apply divide and conquer method. Divide and conquer method in the sense, when values of n is more than 1, greater than 1, in that case we have to divide the problem into 2 sub-half problems. Okay, left side problem and right side problem. Okay, so in that case what happens, if the element is only 1, we say that element is a key element. If the element is more than one, maybe it can be 5 elements, or it can be 10 elements, or it can be 50 elements, etc. We have to divide that particular element. If n is more than 1, okay, we have to 0, n is there, we have to divide that particular element. Okay, so this is left sub problem and this is right sub problem. And this is right sub problem. Okay, so what happens here is, so during that identification of the key value out of the given list, okay, we are not sure whether that element key element exists in the middle element, or less than the mid element, or higher than the mid element. For that purpose, we have to check this condition. If element is only one element, okay, so in that case my key element is found at the first instance itself. When n is equal to 1, my first instance is nothing but your element is found. Okay, at the first instance itself my element is found. Suppose if you take the second condition means what? Whether my element is, suppose left side, in that case what happens? You have to search left side the element. So what you have to do is, you have to identify the mid value. Mid is nothing but your low plus high by 2. Okay, because of this low plus high by 2, I am going to partition my array element into left sub array and right sub array. Okay, in that case what happens? For this condition, if x less than a of q means, if my key element is falling under left part of the list of the array or not, I have to check. For that purpose, I am going to check here. third one is, suppose if my element is falling right side, key element is coming right side, I have to check right part. In that case, low minus q, q plus 1 means what? My mid plus 1. This is my mid plus 1. This is my mid plus 1, this is my mid minus 1. Mid minus 1 is nothing but left side and mid plus 1 is nothing but right side. So if my key element is found right side, I will be checking recursively right side. If my key element is found left side, I will be checking recursively my key element left side. That's what I just told, right? You are going to divide the mid value by 2 and you are going to get two different sub problems. And whenever we write an algorithm for binary search, there are two methods. One is recursive method and iteration method. We are going to see both the methods now. In this example, if you can see, I have the name of the algorithm binary search. Array is there, the first index of array, the highest index of array. X is nothing but your key element, what you are supposed to check in the given set of elements. If the loop stops here, the binary search algorithm starts from here onwards. If L is equal to I means what? If my large is equal to 1 means if my element is only 1, in that case my array is having that first element itself as a key element. Suppose in that case I am going to return it. Suppose if my element is not 1, it's greater than 1, in that case what happens? I have to come to the mid, okay, whatever the value I am going to take, I come to mid. Mid is nothing but low plus high, okay. I is nothing but your this value, first index value. L is nothing but your large value. So I plus 1 by 2, my mid value will get it. You will get your mid value. Suppose if you take 0, 1, 2, 3, 4, 5, okay. I have 6 elements, okay. 6 by 2, okay. 6 by 2 is nothing but 3. 0, 1, 2, okay. 3. In this case, the mid will come here. The mid will come here. That mid is identified here. That mid is identifier. After that, what you are going to check it is, if my key element is found in the mid, whatever the key elements, suppose 3 is the key element. If it is found in the 3 or not, I am going to check. If it is found, I am going to return that as my mid element. My key is found in the mid element itself. Okay. Next, if my key element is not found in the mid element, either it should be left side or right side of the element of the array. In that case, if my x of less than a of mid means what? This is mid value, okay, this is mid value. In that case, I have to search left side for the elements. In that case, return binary search, a recursive call goes to binary search, array, index, mid minus 1. Mid minus 1 means this side. Mid minus 1 means left side, comma x. X is nothing but key element, okay. I will be recursive checking the element at the left side. Suppose, if my key element, whatever I am looking is, it's not at the left side, I have to check the right side. In that case, a recursive call goes to binary search, again array mid plus 1, comma L, comma x. L is nothing but the highest element of the nth value and x is nothing but key value. So I am going to search my right part of the array, to check the key element. The same explanation what I have explained here, given it as an example here, I would like to search for element number 78. Okay, I would like to search for an element of 78. I am going to check whether my 78 is falling left side or right side. Obviously, when you find this mid value, after finding the mid value, the 78 falls under the right side. Okay, then I am going to check whether my 78 is coming left side or right side or not. 78 is greater than 43. In that case, definitely my 43 is less than 78 because 78 falls right side of the given set of array. So my comparison has to be checked in the right side part. Then again I am going to check with the new value 66 with 78. Again my 78 is bigger than 68. I am going to check at the right side. Finally, when I calculate my mid value, okay, in that case 78 is there. 78 is already is the right side because of this condition. So when I compute my mid value, okay, 0 plus 1, okay, last one is the value is there, divide by 2 if I do it, I will get this particular index value, okay. This index value is what? 0, 1, 2, 3, 4, 5, okay. 5 means what? 2 will be there. In that case 2 means 0, 1, 2, at this position I am going to get my mid value. So my mid value is found. Okay. So at each instance, starting from this end till end, we have to keep on compute the mid value. Mid is nothing but L high plus L by 2. Okay. Low plus L by 2 or low plus high by 2, whatever it can be. Based on that, you can keep on calculating the mid value. If the key item is found in the mid value, I am going to compute the mid value. Suppose if it is falling left side, I have to check left side. If it is falling right side, I have to keep checking the right side part. The same thing, here we are going to see an iterative version of the algorithm. The same logic, low starts from 1, high is there. Okay. I have some set of array elements. Okay. Starting from 1, here n is there. For this I have given my low value, for this I have given my high value. Okay. And I am checking while low less than high means what? When 1 less than n, if I check, n can be 10. 1 less than 10, definitely it's true. In that case, I am going to compute my mid value. Okay. Then computing the mid value, I am going to get somewhere the mid value here, somewhere in between. Okay. In that case, I am going to check whether my mid value, the key element is left side or not. So I am using that mid minus what. If it is not found in the left side of my elements, I would like to check at the right side part of it, mid plus 1. In that context, you can see I am checking the mid plus what, right side of the element. Finally, I am going to return the mid value if the element is found in the mid itself. So the same explanation what I have explained here, I have shown in the animated version of it. Okay, we have the min. Min is nothing but your low. As per the algorithm is low. A max is nothing but your high or large. You can see at every time I am going to compare with the index and the elements. Okay, I am going to check the max mid value. Based on the mid value calculation, I am checking whether my element is found or not. Based on that, I keep on checking. The moment I found the key element, it says my item is found. So in that case, search is successful. 57 is found in the key element. So this is about your binary search, recursive algorithm and iterative algorithm. Then what I explained now, it is given in a handwritten format. We have the mid is equal to start plot end. We are going to compute the mid value. After finding the mid value, we are going to compare whether the element falls on the right side or whether the element falls on the left side or not. Then there are two examples we have taken. One example, whether 25 is there in this list, it's going to be successful search. It's going to be successful search. Another example, if you take 26 is given here, 26 not there in the list. In that case, it can be, it is not, it says element is not found, -1 is returned, -1 is returned. Then a typical algorithm for binary search, we have the binary search array key element start and end. We are going to check with the mid value and the base condition, and here the derived condition is nothing but your recursive call. The base condition is this one, array of mid is equal to x means what? If the element is found in the mid of the element of the array, we are going to return it, or else we have to keep on checking the recursive call left side array in array key element start mid -1, array key element mid +1 and end. Then we have to calculate the time complexity part of the binary search. Okay. See, in terms of time complexity, if you take T of n is equal to T plus T of n by 2. Okay. Since it's a binary search, we have to apply recursive call here. So for the recursive call keeps on divides n by 2, etc. It keeps on happens until some empty number of times. It keeps on happens, and somewhere we have to generalize the equation. By applying the logarithmic equations or summations equations, etc. So once you consider those kind of I can say replacement of the logarithm or the summation expressions, we are going to compute T of n is nothing but big O of log n to the base 2. This is nothing but the linear value. This is nothing but your linear value. There is a difference between linear value and exponential value. Example, if you take n is equal to 5, if you take linear, n is equal to 5 only. Suppose if you take exponential or factorial, if n is nothing but 2 square, 5 square is nothing but 25. If you take 5 factorial, it's nothing but 120. So always the exponential factorial value will be more than compared to your linear value. So if you can see that in our algorithm chart, which is there in your syllabus, okay, the x and y axis will be there, okay, as the value of n square, n cube, n to the power of Mentasa exponential values keeps on increasing. Accordingly, you can see in the horizontal way, the values also getting staggered up, okay, values are also getting staggered up. So the next topic in this discussion we are going to have it is linear search. Linear search, what happens here is, we have some set of elements. Out of the set of elements, we are going to find the key element is found or not. Okay. For I is equal to 0, okay, here we have data of I array variable, n is nothing but your integer variable and x is nothing but key value. I am going to check from 0 to n number of times whether my key element is found or not. Data of I is nothing but key, x means I am going to check this umpty number of times. N is equal to 5 means 0, 1, 2, 3, 4, 5. It may have some 10, it may have some 5, it may have some 6, it may have some 12, it may have some 18, it may have some 20, etc. My key element is what? 13. If I in that case, okay, I am going to check 1 time not exist, 2 time not exist, 3 time not exist. Yes, 4th time my key element exists, it returns I. Okay. If element is not there exists, it says -1. -1 means what? Failure. Okay. My element is not found. That is the understanding. Okay. What I explained now in this particular example is given here animated way. My key element here is to find 11. I am checking 20. No. 10. No. 7. No. 30. No. Yes. 11th is a key element is found. I am going to print it as my outer element is found. These are the index 0, 1, 2, 3, 4, 5, 6, etc. At the 4th index, my key element is found. My 11th value key element is found. So this is about your the PPT session about your lab program. Now I am going to explain the code of the first program. This program, what exactly it says is all about is a binary search. You have to apply a binary search or linear search, and depending on the condition, depending on the switch condition, whether you want to go for a binary search or a linear search, we can go for a condition. Based on that switch condition, you can go and apply that particular algorithm. Here we have initially declared the header files, stdio.h, standardlib.h and op.h. These are the typical examples or typical declaration of header file, and we have two functions here, binary search and linear search. It has its own parameters, low, high, key and array of elements, and linear search, number of elements, key element and array of elements. Okay. So coming back to the main program, whenever we execute any program, the execution starts from the main program. Here we have some local declarations, pointer variable, n, flag, we'll come to know later why we are using it, key, temp, ch and j, and double s comma us means these for seconds, these for microseconds, and this is for milliseconds. These two variables were used just to check for the time complexity of the algorithm, what is going to be executed here. Struct time val, struct end value. Okay. These both are nothing but structure variables of time val structure, which is already inbuilt in hop.h header file. Okay. Using this variable, we are going to access this particular structure. Okay. Now, in this program, we have two conditions, one is for binary search, another is for linear search. Okay. If flag is 0, you will come to know later why we are using the flag here. In this case, there are two conditions. One condition is for binary search, another condition is for linear search. In this condition, if I opt for the switch condition 1, okay, if I opt for the switch condition 1, enter the number of elements, calloc is nothing but a dynamic memory allocation. From the heap memory, we are going to allocate a memory for the n elements here. Okay, suppose n is equal to 10. From the calloc, dynamic allocation of memory. Suppose n is equal to 10 means 10 into 2, 20 bytes of memory will be allocated in this particular variable. Okay, I am starting my get time of date, ampersand start comma 0 means I am referring to the local time of the system. We are not worried about the time zone, whether it is Kolkata or some other country's origin. Okay, Greenwich Meridian time. We are not worried about time zone. Okay, so with the for loop, I am going to randomly generate some values within the range from 0 to 999. Okay, so those values are stored in this A of I. I am going to print it. whatever the random numbers I have taken it, those random numbers are going to be printed. Okay, those random numbers are going to be printed in A of I array. Now after that I have to swap those random elements to be printed in a sorted order. Okay, I want to sort those random numbers to be printed in a sorted order. In that case, I am using this to for loop, I and j for loop, to compare the elements. Then if the comparative elements are going to be swapped, I am going to use a third variable called temporary variable to avoid overlapping. I am using this particular temporary variable. So while swapping, my elements which has to be swapped will be stored in temporary array. Again, the location where my elements has to be placed, I am going to transfer there. Again, my temporary array variables used to rechange the previous element space. So in that case, after doing this particular swapping operation, I am going to display my sorted order. See, in this case A of I, the random numbers are stored and we are going to print only. But after this for loop, the element which is generated by random number or sorted, that element is printed using A of I. For the same reason, I am using this for loop. Okay. So in that case, excuse me. If I am going to select for the binary search, I am going to enter key, ampersand of key. So whatever the elements I am going to use it, suppose 0 to 10, 0 to 50, 0 to 100, etc. That key value I am going to check, okay, using this scanf. I am going to enter. While after entering from 0 to n minus 1, I am checking in the array my key element. So you can see here the flag will store this binary search function starting from 0 to n minus 1 and key value and array of the elements. So get time n means between this range of starting of my time complexity. Here my algorithm starts time complexity. After all this sorting, etc., binary search, etc., I am going to ending my algorithm. Ampersand end, comma 0 means what? Current stop of the end of the time complexity of the system, okay, of this algorithm. Then I am going to print after stopping that particular capturing the time complexity of this particular binary search. I am going to print the values in terms of seconds, in terms of microseconds, and in terms of milliseconds. I am going to print it up. Okay. After printing it up, I would like to freeze the, or I can deallocate the memory which was taken care by the A, which was taken care by the element A. You can see here A of I will have the random elements. So that much of space should be freed off, okay, or deallocation should happen. Because of that, I am using a dynamic allocation memory function called free of A. Okay, in that case, I have freed it. If flag is equal to 1 means what? If my flag is equal to 1 means what? My element is searched. Okay, my element is searched successfully. So the call goes to this particular binary search. Okay. So the moment I have n elements, the call goes to binary search. In binary search, if elements are more than 1, mid is equal to low plus high by 2, I have to obtain. Okay. So if low crosses high means what? There are no more elements in the array, so I return minus 1. If my key element is found in the mid element itself, I say return 1, successful search. If my key element is left part of the array, then in that case I have to find the binary search recursively low comma mid minus 1 comma key comma A, left part of the array. If my element is not found in the left part, it is existing in the right part of the array, again I am going to check my element exists right or not. In that case, mid plus 1 comma I comma k comma j, I am going to perform. So based on this particular binary search operation only, we'll come to know whether my element is found or not. If my return value is 1 from that particular binary search algorithm, 1 means what? Successful search, element is found. We say element is found and we are going to print the milliseconds of time is taken to search that element and it's going to be displayed. Suppose the condition is 2. Suppose condition is 2. In that case, same logic, same linear search, I am going to call it. I am going to call that particular function start. Okay, number of elements I am going to take from the dynamic memory allocation with the help of calloc. Okay, I am going to use this time complexity system call ampersand of start. This will invoke that time val. This will invoke that time val structure. Which will give the seconds, microseconds and your milliseconds value. Okay. So in that case, I am going to generate the random numbers. The random numbers are stored in A of I. I am going to print it off. Okay, after printing it, I am going to search for the key element. So the moment linear search n comma key comma a comes here, the call goes to this particular. I beg your pardon. Okay, it searches here. It's the code itself. It searches for flag is equal to 1. If search is successful, I am going to print it. If search is unsuccessful, if the element is not found, it says element is not found. Okay. So this part of execution is for linear search, and this part of execution is for your binary search. Okay. So what we have seen here in terms of binary search and linear search means we are searching for key element. If the element is found, we say it's found. If element is not found, we say its element is not found. Okay. This will keep on running until the while condition is not equal to 3. Why means the condition 3 in the while loop is given as exist. The moment you select the third option from the switch statement, will come out of the program. Hope so this particular explanation will give clarity on how a linear search and binary search algorithm is applied in the lab program. In this, we have just copied the program into the online compiler, okay, C programming compiler. I pasted the program here, the same which I explained in the Word document. You can see here I use some online compiler, okay, the same program, binary search and linear search. I copy pasted in online compiler. Okay, you can see here I am going to give the option here. 1. Okay, I am going to give the option here 1. I say enter. Okay, then number of elements is asking. I am just going to give around 25 elements are given, enter. Okay. The 25 elements which is displayed here, which is not in order, randomly generated number, and you can see in the second part of the list here, the elements are sorted. Suppose if I want to find 59, from this given list of elements, I have to just give here 59. If I give 59, I say enter. Okay, so my 59 element is found because it is there in the list. According to, you can see seconds, microseconds and milliseconds time complexity involved in finding that particular 59 element. Okay, suppose if you take second option, okay, for linear search, enter. Okay, number of element I say around 25 again, say enter. Okay, when I say 25 again, these are all the elements which is generated. Okay, suppose if I want to check whether my key element 67 is exists or not, okay, I'll just say enter. Okay, my key element is found successfully. I am going to end the time complexity. Okay, this is about your, and the last option is third option. Third option says exit, and you are going to exit from the console. This is about your binary search and linear search algorithm with time complexity explained to you people. Thank you so much.